Today in the menu we have updates for N64 and Dreamcast. First I'll walk you through the gameplay and design changes affecting all platforms. Then I'll dive into the technical side on how I got this running on the N64, and finally I'll give you a brief update on the Dreamcast version. This is the first iteration of the opening level. You've crash landed here with your companion, and this area will serve as the game introduction. The UI is now much slicker, featuring new sound effects and animated elements. I have also updated the dialogue system. Characters can now have multiple lines of dialogue that cycle as you interact with them. I've implemented wall sliding, which makes wall jumping feel a lot more fluid. I have also added a few cinematic tutorials to help guide the player. Here's another tutorial. You can now enter some buildings like this up here, but I haven't implemented the actual shopping menu just yet. Also, there are some posters and papers on the floor, but they aren't displaying correctly right now due to C fighting. So my next step is implementing proper decal support. I've also added positional audio. Now sounds will gradually fade in or out based on your distance, like the water you hear here. Also previously you could only swim on the surface, but now you can dive deep and explore on the ground. By default, the engine doesn't support some transparency, but I'm looking into making some exceptions to get the water looking better on the N64 or some other platforms. I also still need to implement caustic lighting and vertex displacement for the water's surface. Okay, now let's move to the technical part. The first major fix I tackled was the subpixel precision. Here's a look at how it was rendering before. You can see that jittery vertex snapping effect, kinda like the PlayStation 1. I don't actually use floats for any of my calculations, but that isn't what was causing the snap. The issue was that I wasn't carrying over the 2 bits per component, X and Y, that hold the precision data. So basically, I was shifting the results too far right after the projection, which discarded that extra bit of information. Once I adjusted the bit shifting to preserve those 2 bits, the vertex movement smoothed it right out. When I moved to this new level and tried it out on real hardware, I got this, which is around 20 FPS below target, and that was with some features missing. So there was plenty of work to do to bring this up. My first priority was the textures. I had to ensure that both the modules and the Octree nodes had their materials properly sorted. On the N64, every time you upload a texture to TeamM, you're basically competing with other systems for bus access. So it is always more efficient to group your polygons by texture. The goal here is to process as many triangles as possible before triggering a texture swap. By minimizing those state changes, I was able to get a couple of FPS up. The next step was to C-sort the nodes of the octree. My level is divided using an octree. Octrees divide the space into recursive cubes. The naive approach to render the octree is to iterate through the nodes as they come, make sure they're inside the frustum, and send them for rendering. But there is an easy way to implement the navigation on octrees, so they pick the closer nodes first. This is very important for the N64. When the RTP has calculated the position of the first pixel of a polygon, it checks if the necessary data is present in the span buffer. This is a small buffer that can hold some colors and see buffer data, as to avoid having to constantly bother the main RAM. Once the data is populated in the span buffer, it's sent back to the corresponding color and C buffers. But if we render front to back, then it's more likely the next polygon is behind, so we can save the last step of moving the colors and C buffer back from the span buffer to the main RAM. That gave me between 3 and 4 FPS, so we are now at approximately 18 FPS. Next thing, usually the flow to transform a polygon from world space to a screen space and prepare the command to send to the RTP is like this image below. This is how most libraries do it, including the official ones and the newer ones like Tiny3D. My problem is that the flow of my engine is like the image below. I need to transform and project the vertices, then do some other calculations that are too big to fit in the RSP, and then calculate the coefficients and prepare the command. This was all done in my case in the CPU, and because of those specific needs I could not use any of the current microcode available to manage all that, and I had to create my own. I didn't know much about microcodes for N64, but luckily the same guy that created Tiny3D also created a transpiler to create microcodes. That was great to get a basic understanding, then I could just move to assembly and optimize it further. That gave me around 6 FPS, so we are now up to 24. And there is only one way to make something faster than the fastest possible way, and that's not to do it at all. Even with the frustum cooling and the nodes and the super quad morphing, I still had areas where too many polygons were being processed. To fix this, I decided to implement the software occlusion planes. I can manually place these planes throughout the level. Depending on their orientation, they generate a list of all the polygons hidden behind them. At runtime, the engine iterates through these planes and creates a unified visibility flag for the superquad. If a superquad is flagged as occluded by any plane, the engine simply discards it before rendering. That optimization finally brought the performance up to 30 FPS. There were some extra FPS I could get by getting a better understanding of Flip Dragon, and that brought up this scene to 33 FPS, but I have the FPS limited to 30 because they fluctuate too much and I find it a bit distracting. Good thing is that this whole level with the music, textures, models, etc. is less than 2 MB, so getting to fit a decent amount of levels and still below 60 MB is not difficult. The N64 can manage more than 64 MB, but a lot of the flash cards are limited to that, so I wanted to stick to that size. Now let's move briefly to the Dreamcast version. I had some code for the rendering part that I had written a few years ago. Luckily the API didn't change much, so I could reuse most of it. The game runs at 64 by 480 and 60 FPS. Textures are still 32 by 32. I wanted to try a higher resolution, but I didn't have time before wrapping up this video. I still don't know much about the system, but it seems there is a decent amount of use I'm not being using. so I will try to think of something that could better use the hardware without having to separate much from the other versions. And that's all for now. Thanks for watching and see you on the next video.